People have been arguing for centuries that 0.9 recurring can't equal 1, with simple arguments like it can never reach 1, or how can 0 point something be equal to 1 point something? But mathematicians will tell us that if we accept 0.9 recurring is a real number, then we have to accept that it does equal 1. But what if we don't accept that 0.9 recurring is a real number because we don't even accept the concept of real numbers themselves? This symbol 0.9 recurring was around for over 200 years before it was defined to represent the limit of its partial sums. And this timeline shows the period of over 200 years where unending decimals were not defined as limits. We can't actually draw a line that is exactly the square root of 2 of any unit of measurement. All we can do is draw a line that is close to some value in the sequence of values generated by a square root of 2 algorithm. Such an algorithm can't complete. It can't do an infinite amount of work and say, there you go, I've produced a constant that is the square root of 2. Unlike 0.9 recurring, there is no constant that we can say the sequence is approaching. So the supporters of real numbers have to dubiously claim that they can imagine a final constant, and since they think they can imagine it, such a point must therefore exist. Even some mathematicians now finally concede that the square root of 2 does not exist. How can there be no last non-zero term, and yet the sum of the terms is somehow a static value? It doesn't make any sense. The 0.9 recurring equals 1 debate won't go away while blatant absurdities like this one remain unresolved. This problem was even debated by the ancient Greeks. It was about 500 years BC when the ancient Greeks proved that the square root of 2 could not be expressed as a rational value. The proof could have been interpreted as evidence that such lengths can't exist, but it seemed more reasonable to them to accept the existence of irrational lengths, and that this amazing information was previously only known by the gods. If we accept that a length of exactly the square root of 2 can exist, then it follows that 9/10 plus 9/100 and so on should also correspond to a static fixed length. In which case a journey from A to B should be able to be considered as being a completed infinity of smaller journeys. So when we get past point B, we will literally have gone to infinity and beyond. But just because we know it's certainly possible to move from point A to point B, it doesn't mean that the concept of a completed infinity is the right way to model that journey. The argument that it appears to be successful can't be considered to be a valid argument for using infinity in mathematics. A real number is defined as the limit of the increasing partial sums. And for a geometric series, the limit or sum is supposedly well defined. We can form an expression for the sum to the nth term that simplifies to k minus k times r to the power n, where k is a divided by 1 minus r. The constant part, a over 1 minus r, is called the limit, and in complete disregard of the obvious fact that it is impossible to add up infinitely many non-zero terms, the sum is defined to be equal to the limit. If the expression a over 1 minus r was really the sum of infinitely many terms in a geometric series, then 1 plus 2 plus 4 plus 8 and so on would sum to minus 1. And minus 1 minus 2, minus 4, minus 8 and so on would sum to plus 1. But supporters of real numbers wanted to claim that the expression could be said to equal the infinite sum in some cases, and so they used definitions, notably convergent and divergent, to exclude the cases that appear to lead to absurdity. And so if you encounter a clever sounding argument that relies on the expression for the sum of a geometric series, bear in mind that it is little more than a proof by definition. Next, we have what's called the intuitive explanation, in which the partial sums are placed on the number line one by one, and we consider what distance remains to the point corresponding to the value 1. Generalizing, the distance from the nth term to the point 1 will be 1 over 10 to the power n. So if 0.9 recurring was less than 1, we should be able to find a point that is between 1 over 10 to the power n and the point 1 for all possible values of n. And since no such point exists, the mathematicians conclude that it must equal 1. But here we can use a cat and mouse argument, in which we can easily switch the roles of cat and mouse around by saying, you give me any nth sum and I can give you a point that's closer to 1 than your nth sum. And since this will work for all possible nth sums, points must exist between 0.9 recurring and 1. So these are two equal and opposite arguments. One implies there can't be any points between them, and the other implies there must be points between them. You might think this shows that 0.9 recurring cannot be any fixed value, and if it can't be a constant value, then possibly the most obvious conclusion is that it must be process related. The ignored contradiction is just one of the problems with the mainstream's intuitive explanation. Another problem is that it involves infinitely small points on an infinitely divisible, infinitely thin number line that goes from minus infinity to plus infinity. We can imagine a thick line, but when we try to imagine an infinitely thin line, it completely disappears. Nobody can truly imagine infinitely small points and infinitely thin lines. We can only imagine solid lines and solid dots and pretend that these represent infinitely thin lines and infinitely small dots. And so the belief that it is valid to theorize about such things has to be based on pure faith. And a third major problem is the problem of the last term. Given that all the points in the sequence 0.9, 0.99 and so on are supposedly static points on the number line, then how can there not be a last point? If we approach the number line from the right, then which of these static points will we encounter first? If we approach one from the left, then how can we have passed an infinite amount of these points when we reach the point 1? And how can we not have passed a last point? But the supporters of real numbers just dismiss all these problems, and they restate their intuitive argument as a formal proof that has been accepted by the mathematics community at large. Whereas with the series approach, we can find as many series as we like between 0.9 recurring and 1, such as 95 over 100 plus 45 over 1000 plus 45 over 10,000 and so on, which happens to be exactly halfway between 0.9 recurring and 1. But they will insist that their proof is still valid, because a proof is deemed to be valid regardless of whether or not the premises or assumptions are valid. Just try to get your head around this. It doesn't matter if we wrongly assume that 0.9 recurring is a constant, because the proof that it must equal the constant 1 will still be valid regardless. Perhaps the simplest of all the proofs is the convincing argument that we all encounter at an early age. We are taught that the division process of 1 divided by 3 will yield an infinite result. And it feels right that 0.3 recurring must equal a constant, because we presume that any whole cake can be divided into 3 equal parts. Then 3 times this infinite answer, which is 0.9 recurring, must equal a whole one, just like 3/3 of a cake equal a whole 1 cake. But does the division process really produce an infinite result? After processing n decimal places, there is a remainder of 1 over 3 times 10 to the power n. So there will always be a non-zero remainder. The remainder can't go away. So we might come to the conclusion that 1/3 can't be fully represented in base 10, and that not all cakes can be divided into exactly 3 equal parts. Even though the wider mathematical community concede that we can't actually perform an infinite division, they believe we can still theorise about what the result might be if such a thing could be done. But if we are to believe that we can imagine something as strange as a completed infinite process, then we might as well imagine that we could end up with an infinitesimal, which is equally as unbelievable. And since nobody can actually perform an infinite division, nobody will be able to prove if the remainder goes to an infinitesimal or goes to 0. So it's all absurd. Another common argument is that if we subtract 0.9 recurring from 1, we get 0. Hence, 0.9 recurring must equal 1. But if 0.9 recurring is not a fixed value, and instead it is a sequence, then in order to subtract it from 1, we need to treat 1 as a sequence and perform arithmetic on sequences or series. 1 can be converted to the series 1 plus endless zeros. Then if we subtract the series from 0.9 recurring, we get a new series as the answer. Or we could treat 1 as a sequence, subtract the sequence for 0.9 recurring, and get a new sequence as the answer. Perhaps the best approach is to work with the nth sum expressions. And when we do the subtraction, we get a result of 0 plus 1 over 10 to the power n. Unlike 1 and 0.9 recurring, this result can't be mapped to base 10 place values. This result might describe a series of journeys in the real world. The first value in the sequence is 0.1, and so the first journey could be to a position at 1/10 of a certain distance. The next value is 0.01, and so the next journey could be to the position corresponding to 1/100th of the total distance, and so on. You'll never get to 0 by following this sequence, and so the result is clearly not 0. Another really popular argument is called the algebraic proof, and it goes like this. Let x equal 0.9 recurring. So 10x is 9.9 recurring. Then we subtract the first line from the second, giving 9x equals 9. And so x must equal 1. This might look very clever, but just think about what's really going on here. We start with x equals 0.9 recurring, then all we do is simply multiply both sides by 10 minus 1 divided by 9, which is the same as multiplying both sides by 1. So we should end up with exactly what we started with. It shouldn't change to x equals 1. If we multiply both sides by 9 over 9, we get 9x over 9 on one side and 8.9 recurring over 9 on the other. And so this time we do end up with exactly what we started with. Now let's consider the difference between the two approaches. It all comes down to what is 0.9 recurring times 10 minus 1. Does it equal 8.9 recurring, or does it equal 9? The question is, can the subtraction operation somehow get rid of the endless terms? If we work with the series instead of the decimal, we write it down again and note the one-to-one correspondence between the terms. Then we multiply the top line by 10. Note that each term of the series gets multiplied by 10, and we keep the one-to-one correspondence with the original terms. Now we do the subtraction, and the resulting series on the right-hand side is 81 over 10 plus 81 over 100 and so on. It is not the number 9. This would appear to correspond to 8.9 recurring in decimal form. In order to get 9, as in the so-called algebraic proof, we would have to shift the terms, breaking the one-to-one correspondence. And we would have to believe that we can match all the original terms with one less than all the original terms. But can we really do this? We could test if this logic is correct if we could find a case where the trailing part cancels out in both scenarios, when we shift the terms and when we don't shift the terms. And this series, 1 plus 1 plus 1 and so on, just happens to fit the bill. On the left-hand side, we won't shift the terms, and on the right-hand side we will. We'll shift by one place, as in the proof. We'll do the subtractions, and we end up with 0 equals 1, which is a clear contradiction. And so this appears to indicate that we can't match the original terms with one less than the original terms. In which case, the algebraic proof is flawed, and it doesn't prove that 0.9 recurring equals 1. Yet again, the mathematicians will claim that we're not following their rules. But we used the series 1 plus 1 plus 1, etc. to test the logic of matching all the original terms with one less than all the original terms in a subtraction. The only thing that's relevant to the cancelling out is that the series is endless. But the mathematicians will claim that we can't test the logic with a divergent series. It seems like they are still just choosing to rule out any logic that highlights a problem with their precious real numbers. If we have any doubts about 0.3 recurring being equal to 1/3, then we might be convinced by the argument that 1/3 can be represented as a finite decimal in some bases. For example, 1/3 is 0.1 in base 3. And if a third can be represented in one base, then surely we must be able to represent it in any base. And the only representation that it can be in base 10 is 0.3 recurring. But before the introduction of unending decimals in 1594, it was accepted that values like 1/3 could be expressed in some bases but not in others. We can't do infinitely many stages of a division process, or even a base conversion process. But mathematicians believe we can theorize about what the result of such an infinite process might be. So the supporters of real numbers choose to believe that the remainder goes to 0 and that the so-called real number, 0.3 recurring, has to equal 1/3. But if we don't accept that endless decimals are the same as constant values, then there is no reason to believe that all numbers must exist in all bases. The unsuspecting layperson can feel bamboozled by the many complicated sounding proofs, of which there are many, and all of which supposedly provide undeniable proof that 0.9 recurring equals 1. such as proofs based on Dedekind cuts and the equivalence of Cauchy sequences. Not to mention the proof using the nested intervals theorem. The proofs keep coming like paper churning out of a photocopier. Now, if we've already rejected the concept of real numbers, then we're not going to accept these extra proofs which are based on methods for supposedly constructing real numbers. And so there are no significant new arguments here at all. They are just repackaging copies of arguments that we've already covered. We've covered a lot of different opinions relating to the 0.9 recurring issue. These disagreements spill over into disputes about the foundational principles behind all mathematics. The two sides are fundamentally opposed on almost everything, because what makes perfectly good sense to one person will sound like complete and utter nonsense to another. I hope you will go on to discuss the issues raised on other forums, so that we can all help to raise the awareness of these important foundational problems. Finally, if you found this video interesting, then please click like, and if possible, share a link to this video on social media in order to increase awareness and promote further discussion. It would also be great if you could subscribe to my channel. Thank you for taking the time to watch, and I hope you enjoy my other videos.